36.3 is about population growth and how populations change over time. In regards to the equations, as we'll see, I don't think based on the AP Bio questions, there's a lot of emphasis into understanding the details in terms of plugging in the math and determining the rates, really, that I've seen based on my experience in teaching AP Bio, but rather in understanding what the equations mean in a qualitative or conceptual way. So the growth rate per capita individual of a population is the birth rate minus the death rate. If the birth rate is higher than the death rate, the population is growing. If the death rate is higher than the birth rate, the population is shrinking. And so it's the change in the number of individuals over time equals the birth rate minus the death rate. If the birth rate is equal to the death rate, the population size is not changing. So for example, in Niger, the birth rate is about 3%. The growth rate is about 3%. That means every year the population size increases by 3% of what the population is. Growth rate can be multiplied by the population size to estimate the change in population size which will occur. And so the birth rate minus the death rate equals the growth rate, and the growth rate can be multiplied by the population size to determine what the change in the population size per year is. So for example, go ahead and pause this video and calculate the answer to this. Okay, you should have been able to get, hopefully you pause video, and you should have been able to get 700,000. All you do is take 0.0316 times 22.44 million, and you should get 700,000. Okay, so that's the change in population per year. Growth rate can be represented by R, and in ideal conditions, different species have different maximal rates of growth. So the max growth rate a certain population can have is going to differ based on the potential of that species. So fish population might be able to grow at a much faster rate than, let's say, a giraffe. This maximal growth rate is R max. And we can estimate the maximal growth rate a population could grow as the R max times the N, which equals the change in population size, where N is the number in the population. So R max times the population size will equal the change in population size. This is just saying, just like before, that the growth rate times the size of the population will give us a change in the growth rate. So this is saying, how much could the population change maximally? What's the greatest potential change? Exponential growth is when a population grows at an exponential rate. And so the graph looks like this when the growth rate is becoming greater over time. And it produces a J-shaped curve. Logistic growth is when a population grows logistically. At first, there's a little increase in population. Then the population grows rapidly, and finally growth rate slows down. And so this looks like an S-shaped curve, where there's a little bit of growth and then a much more rapid growth, but then the growth slows down as it approaches a carrying capacity. So the carrying capacity is the maximum population size of the species that the environment can sustain indefinitely, given the food, habitat, water, and other necessities available in the environment. So how many individuals can the environment sustain? The population will level out at about that number. Here's an example looking at the wolves in Yellowstone Park I mentioned before. You can see that at first there was a really high rate of growth, and then the population evened out at about some level around some carrying capacity, which looks at about 100 wolves over time. Okay, and so this is an example of logistic growth where the growth was really high, it overshot the carrying capacity a little bit, and then it evened out. To estimate the fraction of a population's growth rate compared to R max, multiply R max by the difference in percent between the current population size and carrying capacity. In other words, if the population is very, very small compared to the carrying capacity, the growth rate will be close to R max. Like at the beginning here, when the wolf population is very small, the carrying capacity is, let's say, 100, and the population is only 20, then the growth rate will be very close to R max. So according to this equation, it would be multiply R max by the difference in percent between the current population size and carrying capacity. Well, if it's 20 individuals and the carrying capacity is 100, then the difference is 80%, right? Because only 20% of the population compared to the carrying capacity is there. So the difference is 80%. So the growth rate would be 80% of R max. In other words, the growth rate would be almost as high as it could possibly be. Whereas once the population gets to carrying capacity, then the growth rate, well, there's not going to be growth. And so if it's 100 out of 100, 100 out of 100 means that there's a 0% difference between them. And so therefore the growth rate is going to be like 0, right? It's not going to be anything because they're already at carrying capacity. That doesn't mean there's not animals that are born and die, but the effective growth rate is 0. And again, from what I've seen, AP Bio doesn't put a lot of emphasis into you plugging and chugging this, but understanding that if a population is a long ways to go before it reaches carrying capacity, its growth rate will be close to R max. Whereas if the population doesn't have as far to go compared to carrying capacity, then the population, the growth rate will be very, very small. If there's no change in the population size, it is 0 population growth. Why does carrying capacity exist? Because of intraspecific competition, when members of the same species compete for limited resources. And so, for example, members of some species defend their territory because there's limited resources available. And so the resources become more limited the more members there are. And so if there's too many individuals, there's not enough food, or there's not enough water, there's not enough shade or habitat or whatever. A classic example is yeast. And when I teach general biology, we grow yeast soda, and the yeast will grow really, really quickly, and then the population size kind of levels out in a population over time because they're reaching carrying capacity. There's only so many resources available to them. Another example is with seals here. So yeast grown in ideal conditions in a test tube show classic S-shaped logistic growth curve, whereas seals show real-world fluctuation where it's a little more random, kind of like as you saw with the wolves. The population goes up and down, but there's some sort of carrying capacity represented by this idea that there's some sort of level that the population will move around, if that makes sense. That is it for 36.3.